Okay, good afternoon, everyone, and good morning to Hugo. And today is the, I think, sixth or seventh episode of the AI Talks series, where we want to keep up with the latest advances in AI. And today we are very happy to have Hugo as our speaker. So Hugo has just finished his PhD, and he's now a research scientist at Meta, focusing on deep learning and computer vision. So in today's talk, Hugo will share his latest research in how to design architectures and training algorithms for visual understanding. So Hugo, you can start whenever you are ready.
Thank you very much for the introduction and for the invitation. So today I will talk about architecture and training for visual understanding. So this presentation is mostly on computer vision, and it can be long to say what is computer vision, but here I provide some example in order to have a better idea of what is computer vision and how computer vision can be used in the real world. So there is a lot of application of computer vision, for instance, in robotics, medical image diagnosis, image restoration. So the application of computer vision can be very diverse. But in a research perspective, generally, we have 4 different tasks: image classification, object detection, semantic segmentation, instance segmentation. There is also some other tasks, but these 4 tasks are maybe the more common task. They are quite different from each other, but generally they are based on the same kind of architecture. There is just some kind of modification, some kind of adjustment in order to adjust the architecture for these different tasks. But generally, the base model that is used are quite similar. And generally, when we design a new architecture, when we design a new base architecture, we evaluate this architecture on image classification task, and in particular on the ImageNet classification dataset. So in this presentation, the results are mostly on ImageNet for image classification task. There is some few experiments on other tasks, but the architecture I will present can be reused in other tasks by just some slight adaptation. So generally in computer vision, we use convolutional neural network, but now it's not really true. To explain that, I will talk about in the first part about architecture for computer vision. After that, I will talk about architecture and training interaction. And in the last part, I will conclude these different points. So first, architecture for computer vision. The 3 October 2020, a lot of people ask if this is the end of convolution, because there is an amazing paper, an image is worth 16 by 16 words, transformers for image recognition at scale. This is the first time that a vanilla transformer reached a state-of-the-art result on the ImageNet classification task. And this is a quite amazing result, because if we look at the history of transformer, this architecture today reached a state-of-the-art result in different fields, for instance, in text, in speech, and now with the Dozovitsky paper, they reached state-of-the-art result in computer vision. Before the Dozovitsky paper, there is some few attempts to incorporate some transformer component in convolutional neural network. So some people try to incorporate some attention mechanism. For instance, this is the case in the ResNet ST paper. Some people try to use hybrid architecture with ConvNet and transformer. For instance, in Dieter, they use ResNet 50 and a transformer for object detection. And before the Dovizovitsky paper, there is some attempt to use vanilla transformer on computer vision, but generally they apply the transformer at the pixel level. And due to the quadratic complexity of the self-attention mechanism, this architecture was not very efficient. Now we have some state-of-the-art result with transformer since the David-Scale paper, but there is a major drawback. You need to use 100 of million of annotated images to reach ConvNet performance on the ImageNet dataset. Typically, the GFT dataset that is a private and only available at Google. So we try to answer the question, can we train an effective vision transformers model without a huge dataset like GFT? So the first idea is to say, okay, we don't have a lot of data, we have just ImageNet 1K, and maybe we can try to use data augmentation to simulate in a certain way more data, and we can try to use regularization to mitigate the overfitting effect. Because with transformer, you have a very general architecture, and generally with this architecture, it's easier to overfit. So we consider different kind of data augmentation and regularization. We consider round augment, auto augment, mix up, cut mix for the data augmentation, and for the regularization, we consider erasing, stochastic depth, repeated augmentation, and dropout. So we try different combination of data augmentation and regularization. And we design, thanks to this different ablation, the first row, that is the DIT training strategy. As you can see in this ablation table, the training is not very robust to the change of some component of the training. For instance, if you change the optimizer, or if you remove, for instance, repeated augmentation, you can have some drop in terms of performance. And in some case, you can have some kind of divergence, for instance, if you remove stochastic depth. But all these results are reached with all the same in parameter in terms of learning rate. For mix-up cut mix, we use just one kind of alpha. So maybe here, when we remove stochastic depth, the model diverges, but maybe by readapting the learning rate, it's possible to have convergence. But as you can see, the training is quite not very robust according to the component we use. So now we have training strategies that works quite well with transformers. But if you look at ConvNet architecture, in the design of ConvNet, there is a lot of spatial prior in the design of the ConvNet. So there is a convolution operation that is very suitable for dealing with spatial data. So we try to reincorporate in a certain way this spatial prior from ConvNet. So to do that, we use knowledge distillation. So thanks to the knowledge distillation, we will want to introduce some soft spatial prior from ConvNet in the transformer architecture. So we can, the first idea is just to try to use the classical soft distillation loss, that is right here. But when we do that, we don't have good performance, maybe because the soft distillation loss is not very close to the classical cross-entropy loss, and the training of transformer is not very robust to change of hyperparameter, change of the loss. So maybe to have good performance with this loss, you have to adapt a lot of hyperparameter in the training. But we don't want to do that. Therefore, we try to design a new distillation loss closer to the classical loss without distillation. So we use just an equal ponderation between the classical loss, so the cross entropy with the ground truth labels, and the cross entropy with the argmax output of the teacher. And this new formulation of the distillation loss worked quite well, because in that case, we are quite close to the classical cross-entropy loss without distillation, so we don't have to readapt all the hyperparameter. And the other idea we have for the distillation is to introduce a distillation token in order to avoid some bad interaction between the class token and the distillation part. So the goal of the class token is to aggregate thanks to the self-attention mechanism to aggregate some useful information to find the Prontools label. And the goal of the distillation token is to aggregate the information in the self-attention layer to be able to have good feature to reproduce the teacher output. So we try different kind of teacher, and as you can see in the first tab, GoogleNet teacher are better. And it's quite useful to use hard distillation instead of soft distillation. And it's better to use a distillation token. As you can see, we can have some boost in terms of performance, maybe because it removes some bad interaction between the class token and the distillation token. And we can see, maybe we can see that like a kind of ensembling, because class token and distillation token learn a feature in a different way. So at the end, merging this feature just by an averaging help to have some kind of boost, maybe because they are in a certain way complementary. So thanks to this new training strategy, thanks to the distillation, we have performance comparable to GoogleNet with just ImageNet 1K dataset for the pre-training. So it's quite interesting results. Now I will try to explain why hard distillation works, because we can think if we have the optimal teacher with the 100% accuracy, it will be similar to use the ground truth labels. But in fact, it's not really true, because during the training we use data augmentation, and with transformer, in order to avoid overfitting, sometimes we use very strong data augmentation. And one main drawback of strong data augmentation is it can corrupt the labels. For instance, here, this is a simple example with random resize crop. So if we suppose this is the original images with the label zebra, there is a lot of images on ImageNet with the two different concepts in the image, but we have only one label. If we apply random resize crop on these images, we will first select a crop in the images randomly, and after that we resize the crop. So typically we can have this kind of result. So in that case, the data augmentation will corrupt the labels. If we have just this image, we have just the giraffe concept in this image, and it's the zebra concept is not relevant. And thanks to the teacher, we can correct that. So in a certain way, the teacher can help to compensate the corruption of the label due to the data augmentation. And it can also help to correct some bad annotation in the dataset, because in the ImageNet dataset, there is some error in the annotation. So at the question, can we train an effective vision transformers model without a huge dataset like GFT? The answer is yes. If we use the right training strategy, the lack of data can be partially compensated by more regularization, data augmentation, or distillation. There is a lot of subsequent work that reuse the DIT training strategy to propose a new transformer architecture for image classification on ImageNet with pre-training on ImageNet only. But now, if we look at the Dozovitsky paper, if we look at figure 8, we can see increasing the depth can help to have a better accuracy efficiency trade-off. So we try to increase the depth of the DIT architecture. But for instance, if we take a DIT small and if we increase the depth from 12 layers to 24 layers, we have some instability. So the models diverge and we don't have very good performance. So it's not possible to train a deeper architecture with the DIT training strategy. It's unstable. So we try to answer the question, how to train deeper vision transformers. The first idea is to say, okay, in DIT, we have stochastic depth. With stochastic depth, in a certain way, we can simulate architecture with less layers. So maybe just by adjusting the stochastic depth coefficient, it's possible to train deeper architecture, and it works. As you can see here with the DIT small, if you adjust the stochastic depth to rate, you can train a deeper architecture. But maybe it's not really optimal, because if we look at the NLP architecture, there is different methods that are proposed to train deeper transformer architecture. For instance, ReZero, FixUp, FixUp. But in this method, they remove layer norm, warm up, they introduce different scalar multiplier in the residual block with needs that depend on the depth of the layer. But in this setting, it doesn't work. In order to have a good result with this approach, you have to add the warm-up and the layer norm. Otherwise, it doesn't converge. But if you do that, you have quite good performance. It's slightly better than just a stochastic depth. But this approach are quite complicated because you have different multiplier in the residual block. You have to adjust the initialization according to the depth of the layer. So we try to simplify that. We just propose to multiply the output of each residual block by a diagonal matrix with a learnable weight. And we call this method layer scale. And it works quite well. The performance are slightly worse for non too deep architecture, but are slightly better for deeper transformers. So here you have a plot of the stochastic depth with different coefficients and the use of layer scale, because when you use layer scale, you have to use a different stochastic depth coefficient. And in this figure, you can see with more depth, it's important to increase the stochastic depth coefficient. So the question, how can we train deeper vision transformers? The answer is with layer scale and stochastic depth. Now we have transformer with good performance on ImageNet dataset with just ImageNet 1K for the pre-training. We are able to train a deeper transformer architecture with layer scale and stochastic depth. But now the question is attention necessary? Because as you can see with transformer, we don't have just a new architecture, we have also a new training procedure. So maybe the self-attention mechanism is not the main point that allow transformer to have very good performance on ImageNet. So we try to see if it's possible to simplify this architecture and to try a kind of MLP architecture by patches. So in that case, we just remove all self-attention layer in the transformer and replace this multi-head self-attention layer by just one linear layer. So it's typically an MLP by patches. One advantage of this kind of architecture, it's very easy to visualize after the training the linear layer weight in order to understand how the architecture spatially preprocesses the images. And as you can see here with the ResMLP architecture with 24 layers, at the beginning, the network learns some kind of convolution. According to the depth, the kernel of this convolution are increasing. And at the end, we have some kind of long-range interaction. So with this MLP architecture, we have quite good performance on ImageNet, but it's slightly worse than a pure transformer architecture. But something that is interesting, if you remember the previous slide, the linear layer learns some kind of convolution operation. So maybe it can be interesting to replace this linear layer by just some convolution. And it works very well. In fact, you have better efficiency accuracy trade-off by doing this replacement. So at the question, is attention necessary? The answer is no. Splitting images in pages and training procedures seem to be the key elements. Nevertheless, attention remains more effective than a simple linear layer. So we have tried to replace the linear layer in ResMLP architecture by convolution. Now we want maybe to try to design some kind of convolution convnet by patches, but very simple convnet, so with no pooling layer, with just one kind of convolution. The idea here is to try to answer the question, is it possible for a convnet to work with patches? Can they have similar property to transformers? because one very interesting property of transformers is attention map, because thanks to attention map, you can see how the network aggregates the information to produce the prediction and what are the more important parts in the images. So we try to design a learned aggregation operation. Typically, it's just a self-attention mechanism with only one head, and we use this mechanism instead of the average pooling. So we can see that like a learned aggregation layer. And thanks to that, it's possible to have some kind of attention map with GoogleNet. So we tried that with the classical ResNet 50. It worked quite well, but unfortunately, with the ResNet 50, we have some pooling stage. And this pooling stage introduced some kind of artifact. As you can see in the corner here, you have some kind of artifact. So we tried to design a GoogleNet, a very simple GoogleNet by patches without a pooling layer. And we call this architecture patch GoogleNet. And as you can see, by removing the pooling stage and just by using a GoogleNet by patches, we have maybe better visualization. And we want to go beyond that. And we try to use one class token by concept in the dataset. And this is the result in the last column. Thanks to that, you are able to separate in the attention map each concept, so you can have a kind of weak segmentation. And it's quite interesting to understand where are the interesting concepts in the images and what patches are relevant for this concept. It's particularly interesting because it can help to understand the prediction of the model. So here the idea is to train the network on ImageNet, and for each images in the validation set or images from the internet, look at the top 3 prediction and look what are the pages used to make this prediction. For instance, if we take the first images here, the top 3 prediction are grocery store, orange, Granny Smith. And if you want to understand why the network say grocery store, you can see, thanks to the attention map by concept, that the network mainly focus on the different type of fruits. And thanks to that, the network predict grocery store. But the network predict also orange because it focus on the orange part of the images. And for Granny Smith, this is similar. It focuses on the apple in the images. So this kind of property can be very interesting to understand and interpret the prediction of the network. For instance, with the second images, we can have different concepts in these images. We have volcano, lakeside, valley. So maybe on the ImageNet dataset, the label of these images will be volcano because maybe it's a more important concept in the images. But if the network say lakeside, it's not wrong. And thanks to this attention property, you can see what are the pages involved in the lakeside prediction. So it can be interesting to interpret the prediction of the model. It can be interpret the prediction, especially if there is some error or if there is some kind of strange prediction. So the question, is it possible for GoogleNet to work with pages? The answer is yes. Can they have similar property to transformers? The answer is also yes. We just have to add a sample learn aggregation model. Now we'll talk about architecture and training interaction. So we talk a lot about architecture, but does the training design matter as much as the architecture design? If we look at the ImageNet classification results, year after year, we have new architecture, better and better. But generally, with this new architecture, we have also some new training procedure, but there is more focus on the new architecture than the new training procedure. Here, I like the ResNet 50 because the ResNet 50 is a very common baseline and maybe the more common baseline in computer vision paper. When you propose a new architecture, generally you compare your new architecture with the ResNet 50 performance. But when you compare architecture and when you have an accuracy with an architecture, you have to take into account different components, not just the architecture, because you have the architecture, the training procedure, and generally you have some noise and imperfect measurement due to some kind of overfitting, especially on ImageNet, because on ImageNet, generally we report result on the validation set, and we also use the validation set during the experimentation in order to design the training procedure. And we evaluate very frequently on this dataset, so we can introduce some kind of overfitting. So it can be interesting to take this into account. If we look at the different training receipts for ResNet 50, there is the original one with the 75.3. There is the PyTorch one. Maybe the PyTorch one is the most reported in the paper with 76.1, but it's possible to it can be interesting to revisit the ResNet 50 training receipts, because generally when we propose a new architecture, we train this new architecture with modern training receipts, and maybe the original ResNet training procedure and the PyTorch one are a little bit outdated. So it can be interesting to revisit that with modern training strategy in order to have better comparison between the ResNet 50 and the new architecture. So we designed 3 different training strategies. A1, the goal of A1 is to have the best possible performance. Therefore, we use 600 epochs, so it's quite big in comparison to usual training. We design also A2 with 300 epochs, so it's more common. For instance, generally transformers are trained with a 300 epoch, so this training is closer to usual training used in different computer vision paper. And A3, in order to have fast training, so with A3 we have only 100 epoch, and we exploit the fixed stress effect in order to have faster training because we train at lower resolution. Now the question, and now we want to understand what are the interaction between architecture and training. So we take the A2 training procedure designed for ResNet 50, and we train ResNet 50 in VIT small. And we have this conclusion. So it seems ResNet 50 is better than VIT small, and the comparison seems to be fair because we use exactly the same training procedure. But if we do the opposite, if we design a T2 training procedure, especially designed for VIT small, we have this result and we can have this conclusion. VIT small seems to be better than ResNet 50, and the comparison seems to be fair because we use exactly the same training procedure. So there is strong interaction between architecture and training procedure, and maybe the best way to compare the two architecture here is to use the optimal performance reach for each architecture. But in practice, it's not possible to be sure to have an optimal training for one models, because maybe in the future we can design new methods that can allow to have an optimal, a better training for this kind of architecture. And it can also be computationally prohibitive, because if you have to readjust all hyperparameter, all training components for each baseline you consider in your paper, it can be very expensive in terms of experiment, in terms of compute. So there is strong interaction between architecture and training, but it can be hard to take properly this into account in practice. Now we will focus on the noise in the measurement. So we consider 3 different evaluation setups. We have the classical one, the ImageNet validation. We have ImageNet real that correspond to reliabilization of the ImageNet validation dataset. With sometimes multi-concept for some images when there is a different concept in one images. And we have ImageNet V2. It can be seen as a second validation set of ImageNet, because in order to design the ImageNet V2 validation set, people try to use the same pipeline as the pipeline used for the ImageNet validation set. So it can be interesting to to use this data set in order to have a separate test set. So we perform experiment with 100 different seeds, and we report mean, standard deviation, max, and mean. And we also report the result with seed 0 because we use a seed 0 in all the experiment, in all the ablation in order to design the training procedure. And there is a lot of chance of overfitting with seed 0. And as you can see here, in fact, we overfit with seed 0. It's slightly better than just the averaging over 100 seed. But something that is interesting is with ImageNet V2, we don't overfit with seed 0. And in fact, if you compare the performance of ImageNet V2 according to the performance on ImageNet Val with 100 different seeds, you can see there is no clear correlation. So it can be very interesting to use ImageNet V2 in order to evaluate the level of overfitting. So at the question, does the training design matter as much as the architecture design? The answer is yes. Training gradient has a very large effect on performance, possibly more than the architecture. And now the question is N4 vision transformer. Because with vanilla vision transformers, we have a very general architecture. With the self-attention mechanism, we can learn some kind of convolution, some kind of long-range interaction. So it's a very general architecture with very few spatial prior. Since the Dozovitsky paper, there is few papers that were focused on the training of transformer, but there is a lot of papers that try to design new transformer architecture, sometimes by injecting some hard spatial prior in the architecture design. But maybe with transformer, the hope is to have a very general architecture, so keep the vanilla vision transformer, and just by adapting the training, try to learn the right operation. Because with a very general architecture, I think that in that case, the training can be very crucial because this is thanks to the training that you will learn the right operation. And with a very general architecture, you have maybe more risk of overfitting in comparison to GoogleNet, where the hard design, where the hard spatial prior incorporated in the architecture limit the freedom of the architecture in terms of capability, in terms of operations the architecture can learn, but I think it can help to avoid some kind of overfitting, some learn of bad operation. So we try to revisit a little bit the training of transformer. And as you can see in this plot on ImageNet 1K, the training can be very crucial because here this is exactly the same architecture we compare. We have just some difference in terms of training. And as you can see, we can have very big gap in terms of performance just by adjusting the training. But it's also true on bigger data set. For instance, on ImageNet 1K, we have also some similar results. So on relatively small, but ImageNet is a really small data set, training is very important for transformer, but on bigger data set, it can be also very important. And we look at if this result transfer on other tasks, and it's true. If you reuse the model I presented in the previous slide on segmentation task, for instance, you can have a very good performance. For instance, with VITB, we have comparable performance with the SWIN, so it's quite interesting results. Now we'll talk about the new training component we reincorporate in the training of transformers. So the first idea is to say, okay, we use RandAugment to train transformer since the DIT paper, but RandAugment was designed for GoogleNet because when RandAugment was proposed, there is just a GoogleNet that reached very good performance on ImageNet classification. So maybe there is some kind of overfitting between the RandAugment design and the GoogleNet architecture. So we try to revisit the data augmentation. And with transformer, if you look at the result of transformer with self-supervised approach, generally they are quite good. So we try to reuse data augmentation closer to the data augmentation used in self-supervised learning. So we just try to use these three different data augmentation: Gaussian blur, grayscale, and solarization. And for each images in the training set, we uniformly select one of these data augmentation and we apply this data augmentation on the image. So it's a very simple data augmentation, but it works quite well and it works better than random augment, for instance, with transformers. But it's not the case with GoogleNet, for instance. With ResNet 50, it's better to use random augment. The other data augmentation we change, it's in particular on ImageNet 21K. Usually we use random resize crop, but one main drawback of random resize crop is can corrupt the label in the images. As you can see here with the zebra and the giraffe, you can select just a part with the giraffe. So random resize crop is very interesting when you have few data because as you can see here on the figure, you have more diversity with the random resize crop data augmentation. But using just a simple random crop, okay, you have less diversity, but if you have more images, it can be interesting because as you can see in this column, with simple random crop, you have less noise, so it corrupts less the images, and it can be interesting to use this data augmentation when you have more images. So we use simple random crop instead of random resize crop on ImageNet 21K training. We evaluate the overfitting of the different approaches. On ImageNet 21K, the approach we propose don't overfit more than other approaches. On ImageNet 21K, we overfit a little bit less. So it's quite interesting results. And so now we have a new training procedure, and generally we think that training procedure is orthogonal to architecture design. In order to highlight that is not the case, we reuse this new training procedure with different transformer architecture. With PIT architecture, we have some improvement, but for instance, with the swim transformer, we have worse performance. So this new training procedure works well with architecture close to the VIT architecture, like PIT, Kite, but it doesn't work very well with architectures that are far than the original VIT architecture, like Swin. So it's quite interesting because it already highlights the fact maybe sometimes we can have some conclusion. For instance, in the swim paper, we have a clear conclusion that swim is better than VIT, but maybe with a new training procedure, it's possible to have an opposite conclusion. For instance, here we are very close to the swim performance with the VIT base. So maybe with better training, it's possible to have a completely different conclusion. So it's very hard to know if a conclusion is robust in a paper. Generally, the conclusion is a conclusion according to the training we consider, because it's very hard, given this result, to have a robust conclusion that hold for every training strategy. So the question, and for vision transformers, the answer is yes, the conclusion is the same. The training is perhaps even more important with transformers. So now the conclusions. Architecture for computer vision can be very diverse. For instance, we can have a vision transformer, we can have a MLP architecture, we can have different kind of vision transformer with some spatial prior with ConvNet block. We can have also some classical ConvNet by patches. Each of these architecture have their own property, but it's possible to reincorporate some attention map property in architecture just by adding a learn aggregation layer. There is strong interaction between architecture and training. Measuring progress is a noisy process and can hardly be perfect. So it's very hard to be sure that a conclusion is robust because we don't know what will be the new training procedure in the future. And maybe with a new training procedure, we can have some different conclusion. Thank you for your attention.
Right. Thanks, Hugo, for the wonderful talk. And indeed, the topics covered in this talk are very essential for, especially for practitioners who are working on transformers and large scale training. So, so now we are entering the Q&A session where the audience can pose any questions about the topics covered in this talk, or any questions that you have for Hugo about perhaps the area, right, in the area of computer vision. So in case you are the first time here, the way to ask questions is to raise your hands by clicking the raise hand button in the bottom menu. So you can see in the menu, you can see reactions. Then you click the raise hand button. And so now I will unmute or yourself. You can unmute yourself and then speak up. So yes, please, if you have any questions from the audience, please raise your hands. It's a very good opportunity to interact with experts like Hugo. So if you are working in a relevant field. Okay, we got Li Wei. I think you can unmute yourself. Yes.
Hi, Hugo. Thank you for a great talk. So I think your presentation is mainly focused on the training recipes for supervised training, right?
Yeah.
Okay, and I have the same conclusion in unsupervised training or supervised training, that the training the architecture also highly interact or correlate with the training recipes.
Could you repeat your question, please?
So I might get the same conclusion that in unsupervised training or supervised training, the architecture also correlated or interacted with the training recipes as well.
So the question is if there is some correlation between the training recipes and the property we have with the architecture?
Yes, in unsupervised training or self-supervised training.
Yeah, I see. Yeah, yes, I think according to the training procedure, you can have you can learn different operation in the architecture, typically for transformer architecture. So yeah, I think if you don't have head node regularization, you can have some learn some byte operations, some operations that overfit on the dataset. But if you have node regularization, if you look at the self-attention in transformer architecture, for instance, generally in image classification, at the beginning, they learn some kind of convolution. And I think, therefore, some people directly replace this block by some convolution, because if you know what is the right operation to learn, if you replace the self-attention block by a similar operation, but that is in hard, that is hard encoded, for instance, by a convolution block, in that case, maybe it's easier to train the network, because this is like a very strong regularization, because if you put a convolutional block in the transformer, it can't learn anything else, because you have the convolution layer, and the convolution layer it'll do some convolution, and it's completely independent to the training, for instance.
So you mean better architecture or better training recipe can benefit more for the unsupervised or self-supervised training? Is that what you mean? Or
I mean that the training is maybe more important when the architecture is more general, when you have a lot of freedom for each block. For instance, with the self-attention block, you have a lot of freedom because you can learn some kind of local operation like the convolution and some kind of long-range operation. I think it's more important for GoogleNet, for instance, because with the convolutional block, you can only learn convolution operation. It's harder to have, not possible to have long-range operation if you have a very small kernel, for instance.
Thank you.
Okay, yeah. So it makes sense, right? So for models with less inductive bias, probably is better for self-supervised learning. So okay, let me see. The next one is Jiahao. Jiahao, you can speak up. You can unmute yourself, please.
Okay, thanks. Hi, Hugo. This is Jiang Hao speaking. I have thanks for your wonderful talk, and I have a couple of questions. First, I want to ask, in your talk, you have introduced, say, the DEIT, which is actually commonly used as the supervised baseline in doing in comparing with actually say self-supervised learning or unsupervised learning. Okay, so and the recent self-supervised learning method like mask image modeling or contrast learning has achieved comparable or even superior performance than this kind of supervised learning baseline. And however, you also introduced your recent work in this year, like the DEIT3, and you show that with a proper training procedure, the supervised baseline can also be strong and also surpass the self-supervised learning method, like the MAE or whatever. So, so what do you think? Do you think self-supervised learning is really better than supervised learning, or this just because the supervised learning does not have a better training procedure or whatever? So can you provide some insights into this comparison between supervised learning and self-supervised learning? Thanks.
Yes, but it's a very, very interesting question. I think today it's very hard to say if self-supervised learning, in particular BERT-like approaches, are better than the supervised approaches. I think there is a main advantage of BERT-like approaches. It's harder to overfit the task because, for instance, when you do some kind of reconstruction, I think it's harder to have some kind of overfitting on this task than just predicting some labels. I think it's easier to overfit on some labels because you reduce each images at one point. But I think it's not very clear today what is the importance of the self-supervised aspect. So the more important semantic bandwidth, more general task, and the part of the optimization. Because as I was saying, with BERT-like approaches, maybe there is less risk of overfitting. And I think it's an important point during the training of transformers. So I don't know what is the part related to the optimization and what is the part related to the really self-supervised part, so the more global task and more important semantic bandwidth. Because for instance, for the moment, I exclude the contrastive approach. If you focus just on BERT-like approaches, something that is quite weird, it's, for instance, with these approaches, generally, they have good performance if they first start to do the pre-training. After that, they do a fine-tuning, for instance, on ImageNet 21K. They do the pre-training on ImageNet 21K. They fine-tune on ImageNet 21K with the labels, and sometimes the fine-tuning is very long. For instance, 90 epoch, it's quite long. And after that, they do a fine-tuning on ImageNet 21K. So I think it's quite a bit strange because maybe the advantage of BERT-like approaches is to be able to use a very large data set without annotation. But today, the very good result we have with BERT-like approaches, you need to have all the labels for each dataset, because when you do the pre-training with the BERT-like approaches on ImageNet 21K, in order to have very good performance, you need to fine-tune on ImageNet 21K with the labels. So it's quite strange. And for instance, if you just use a BERT-like pre-training, if you want to do just an evaluation with a linear evaluation or KNN evaluation, you don't have very good performance in comparison to contrastive approaches. So yeah, it's not amazing on this aspect because, for instance, if you want just to have a very general feature representation, and if you want just to do a small fine-tuning behind that, or just doing some KNN to do some classification on a new data set, you can't really do that with BERT-like approach. So I think today it's hard to answer the question, supervised is better than BERT-like approaches, or BERT-like approaches are better than supervised training. I think we can have better performance in each case because we have to find new training paradigm for transformers, because transformers are very new. We have we have designed a lot of methods for ConvNet, and maybe we have to revisit this method for transformers in order to have better training for transformers. And BERT-like approaches in computer vision are also very new. So maybe we have to find a new way to do BERT-like, to use BERT-like approaches with transformer in order to have better performance. So it's hard to answer the question.
Okay, thanks for your answer. Also, it seems like the training procedure matters more than the architecture design. So, for example, compared with DIT, the DIT3 has a huge performance improvements with some special design like the simple random crop or whatever. So, do you think there exists more suitable training recipes for self-supervised learning, or actually, in more detail, have you tried using this kind of techniques to improve the self-supervised learning, or do they have similar benefits or whatever?
No, I don't try these approaches for self-supervised learning, but I think it can help, in particular for the fine-tuning part. I think it will help for the fine-tuning part. I don't know for the pre-training part. Maybe because the fine-tuning part and the supervised training are quite similar, but for the self-supervised part, maybe we have to do some kind of adaptation, and maybe the DIT3 training recipes are not optimal for in that case.
Okay. The last question is that I also read your previous paper. Large-scale data set necessary for self-supervised learning. Yes, yeah. Actually, it's about the scaling behavior of self-supervised learning. So it seems that recent methods like the mask image modeling may not benefit from a large amount of data. So maybe it seems. Do you think it is more data efficient, or it is drawback of asking image modeling that cannot be scaled up in the perspective of data?
Well, very good question. It can be useful when you have less data. I think it can be useful when you because when you have a very large pre-training, if you have a big gap in terms of distribution with the target data set, I think maybe the large pre-training is not very interesting. It can be interesting to do some pre-training on the data set with the same distribution, and it's possible with these mask modeling approaches. In this paper we do some comparison with the previous DIT training strategy. Maybe it can be interesting to try to revisit the result with the new training recipes, because I think the training recipe can have a very strong effect on the conclusion. So I don't know if the new training recipe can reinforce or change the conclusion. It can. I think it can have a strong impact, and it's hard to say what are the conclusions now and what is the difference.
Yes. Yes, I noticed that in your paper you have said that just by pre-training on a downstream data set, it can achieve competitive or superior performance than pre-training on the ImageNet. This is very impressive. So this may indicate that the large-scale data may not be necessary. So, well, it's very maybe good direction, or the good question remain to be explored in the future. Thanks.
Okay. And then. Right. Okay. I'll lower your hand. And next we have a question from Professor Lee. So Professor Lee, you can speak up.
Yes. Hi. Thank you. Thank you for the excellent talk, especially the data points that are kind of hard to come by in an academic setup. So my takeaway message from your talk, right? So pardon me if I maybe am not getting everything, but the one takeaway message I get is that there's a lot of randomness in those experimental results, and the difference between the max and the mean sometimes exceed 1%. Sometimes people say, if I get 1% improvement on ImageNet, which is a very large data set, then I'm safe. But it's, you know, but that's okay. So within 1%, which is great. But the ImageNet V2, you know, the max is 68, the mean is 67.
Yeah.
So if I look at the diagram on the left, so, and there's still strong interaction between the training technique and the architecture choices. So wonder what you think about this says about, you know, some of the recent quote unquote, you know, progress in those techniques. And if we want to not chase those random noise in our experiments, right? Do you have any thoughts about, you know, how can we do that?
Yeah,
because you know, when we do an experiment, maybe it's good, maybe it's not, but is it really a signal or is it a noise? Sometimes it's really hard to tell.
yeah, I think it's interesting to look at the image for ImageNet classification result. I think it can be interesting to look at ImageNet V2 or performing multi-seed experiment in order to know if the results are significant. Because otherwise, it can be very hard to know if this is an improvement or just noise or just some kind of overfitting. So generally, we run multi-seed experiment and we look at the ImageNet V2 results in order to know if we have really some improvement or if the method is just some noise.
Okay. So you're saying, like, basically we need more data sets.
Yeah, typically we need to have more evaluation, so more data set, for instance, using ImageNet V2, yeah, doing some downstream task in order to see if we have already some improvement. Yeah, I think it's better to have different evaluation setup in order to be sure that there is really some improvement. And it can be very interesting to do some kind of multi-seed experiment in order to know if the results are significant or not.
All right, cool, thank you.
Okay, thanks for the question from Professor Lee. And next we have question from Wenwei. Wenwei, you can speak up and unmute yourself, please.
Okay, thanks, Kaiyang, and thanks, Hugo. I'm Wenwei Zhang, a PhD student in the NTU S-Lab. So I want to ask about, so far, and you have already done many significant works in the architecture design and in the training recipes. So what do you think about the next step, especially for the basic models or foundational models for the vision recognition? Because so far we have already have VIT and it already achieves a very good performance, and now we go further step, we have the ResMLP. So do you have some new insights or some expectations in the future about the architecture design or the training recipes in the vision recognition models? Yeah.
Yes, but for the training, we have to find definitively some new training recipes in order to take into account the overfitting. For the architecture design, I think it can be very interesting to study, like it's already a little bit done, study architecture with vision and text, you know, because thanks to that, you can have some kind of few shot evaluation and sometimes zero shot image classification. So I think it can be very interesting to go beyond the art label imposed by the dataset, and can maybe to help to have a better understanding and better interpretation of the concept in the images. Because I think it's quite hard to collect a very large dataset with precise labels, because sometimes you have different concepts in the images. And I think using vision and text can be very interesting to go beyond beyond that. And for instance, you have some interesting results with clip with some zero shot and some few shot result for image classification. So I think it can be a very interesting way to study models with different modalities. So vision and text seem to be quite interesting.
Oh, okay. So you think that the vision language models specifically, and maybe their training recipes and some new architectures may be very important in the future and worth exploring, right?
Yeah.
Oh, okay. Great. Thanks.
Okay. Yeah, I think when Uno has finished. So next we have a question from Yushi. Yushi, you can unmute yourself, please.
Hi, could you hear me?
Yes, we can hear you.
Great. My name is Yushi also from SLab NTU, and I have a question for about the currently the vision and language models are scaling really large. So in language models, you can see many MOE, like a mixture of experts like models. So do you have any comments on this line of work, and will it be a paradigm in the future vision architecture design or training? So any insights on it?
Yes. Yeah, I think it can be very interesting to study a larger architecture for vision, but yeah, in that case, maybe we have to use a bigger dataset, that ImageNet, and maybe a dataset bigger than ImageNet 21K. But it can be very interesting to study bigger architecture to see if we can have some kind of very general model that can be used in a different task. So maybe in that case, it can be interesting to have a combination with a text modality in order to be able to perform some zero shot and some few shot operation. Because when you have a very large model, generally you don't want to fine tune this model for each task. So it can be very interesting to have a way to use this big architecture on different tasks without the need of fine tuning, or maybe a very slight adaptation, maybe with some layer. So yeah, it can be interesting to study maybe some architecture like the Flamingo one, or architecture like Clip. I think if we want to go with bigger architecture, maybe it can be interesting to have architecture with a combination of vision and text in order to yeah, to be able to reuse this architecture on different tasks without retraining or without fine-tuning this architecture. Like it's done typically in NLP. In NLP, when you train a large language model, you can evaluate the models on different tasks with a few shots or zero shot.
Oh, so if I understand correctly, you think that more task and more data and more modality may be the key to scaling a bigger vision model, right?
Yeah. Yes.
Yeah. Thank you very much. Very rewarding insights.
Okay. Thanks so much for the questions. And any more questions from the audience now? You can raise your hands. If no, we have a last question from Yuan Han, who is probably not in a convenient circumstance to speak up. So he wrote in the chat room. So the question is that usually a downstream task is very specific. So a large-scale pre-trained model like transformer might be over-parameterized to a specific task. So Hugo, do you have any insight on how to find a parameter efficient structure from a good trained pre-trained model to, in terms of for each specific task?
Yes. So in the tracing paper, we try different kind of fine-tuning for the transformer. And when you have a few data for the target task, generally just fine-tuning the attention layer or just fine-tuning the FFN layer can give better results than fine-tuning the whole network. So it can be interesting to try to fine-tune some sub-part of the network in order to adapt this architecture to downstream task.
Okay, I see. Thanks again. So, so if there's no more question from the audience, we may